All right, so hopefully you can now see a first slide, which says filters. And this is the advertised talk title. But then I decided that I wanted to make this the title, which is Time to Change Your Filter. And this title is a little bit more to the point, and I'll give some explanations for this later. So Time to Change Your Filter is the title. And well, I really need to say what a filter is. And I'm not going to do that in my first slide. So I'll do this in the second slide. So this is the, let's see. I'm going to tell you what a dictionary data structure is. And a dictionary maintains some set S of elements from a universe U. And so here's universe U of elements A, B, C, D, and the set S here stores elements A and C, and a dictionary supports membership queries on the set. So if we ask, is A a member of the set S? Well, yeah, A is in the set, so it's a member. Is B a member of the set? Well, no, it's not a member. You see, B is not in the set, D is not in the set, but C is in the set. So this is what we mean by dictionary data structure, and the primary operation it supports is membership queries and a couple others. Okay, so this is a dictionary data structure, and a filter data structure is an approximate dictionary. So it's an approximate dictionary because it supports approximate membership queries on the set S. So if we query, is A in the set? Yes, A is in the set. Is B in the set? No, B is not in the set. Is C in the set? Yes, it is in the set. But the data structure makes a mistake on D. It says, is D a member of the set? The filter says yes, but it's not. So this is a false positive. So a filter is an approximate dictionary that has some false positives. Before I proceed, I think I would like to emphasize as strongly as I can that I like interruptions and I like comments. So if there's a question, if there's something that wasn't clear, or you just want to make some random comment, it's okay, because then I'll actually have the illusion that I'm talking to real people, because for all I know, I'm just talking to myself. So the more comments, the better. And if I don't, make enough puns to satisfy Seth, then throw in a couple yourself as well. Okay. So that is a filter data structure. And let's see, I'm having trouble skipping ahead on my slide. There we go. Okay, so the thing about a filter is that it guarantees some false positive rate epsilon. So if the element is in the set, it's always going to say, yes, the element is in the set. That's a true positive. If the element that you're querying is not in the set, then most of the time you'll return, no, it's not in the set. So most of the time you'll say, no, the element's not in the set, and that's a true negative. And here is the only place where the filter makes a mistake. The element is not in the set, but the filter says, yes, it is. And this is a false positive, and the false positive occurs with probability at most epsilon. So this is what we mean by the false positive rate. And you see there's one-sided errors because yes, there are false positives, but they're never false negatives. And these are the guarantees of a filter data structure. And the reason why we want this is because now it allows the filter to be compact. So, right, so here is a filter data structure, and here's the actual dictionary. So here, this is storing a dictionary with errors, and this is the actual dictionary. When you store the actual dictionary, the space is the number of elements n times log of the universe size. That's the number of bits, which is, and this is kind of large here. Whereas with the filter, it's much smaller because instead of being log of the universe size, it's just log of 1 over this false positive rate. And this is something that's much smaller. And so here's the picture of a filter, and that's the dictionary, which is supposed to be bigger. Originally, this was, this is a sperm whale. And originally, this was a a humpback whale, but somebody complained that a humpback whale is also a kind of filter. And so I decided to make it a sperm whale so there was no ambiguity, because a humpback whale is a filter feeder. Okay, so false positive rates, and so the false positive rate, by allowing the false positive rate epsilon, we can have compact filters. Okay, so the talk so far, I've said what a filter is. Now I'm going to talk about the Bloom filter, which is the most common filter by far. And here's a picture, another picture of a filter, which won't be the last one in the talk. Okay, the classic filter is the Bloom filter. So a Bloom filter is a bit array plus k hash functions. And k is a parameter. In all my examples, k is going to be 2. And so here's the bit array. Right now, this is the bit array when nothing is in the set. And now, if we add an element a to the set, so there are 2 hash functions. The first hash function hashes to position 1. And the second hash function hashes to position 3. So you see we've flipped position 0, 1 into a 1, and position 0, 1, 2, 3 into a 1 as well. So these 2 positions that are hashed to, we make those 1s. And now we have a filter with a single element. Then we add another element c, and if you look here, the first hash function for c hashes to 5, and the second hash to 3. So we take position 0, 1, 2, 3, 4, 5, and turn that into a 1. And position 0, 1, 2, 3, well, actually, that was already a 1. So it stays a 1. And so now this is what the Bloom filter looks like with these elements A and C. Okay, so but again, just to emphasize, this is actually what you see. You see this bit array and the hash functions, but you don't actually know the reasons why an element turned from a 0 to a 1. You just see the bit array. So this is why they're false positives. So suppose that we query, is the element B in the set? Well, B hashes to position 2 and position 5. Well, position 2, let's see, 0, 1, 2, that's a 0. So already, because we know that that's a 0, we know that this element B cannot have been in the set. So when you query member B, is it in the set? The filter says no, because one of these bit positions is a 0. If it were in the set, all of the bit positions would have to be 1. All right, so this is what happens if you query, hey, is member B in the set? So then maybe you query, is member D in the set? And let's see, is D in the set? Well, D hashes to position 3 and position 1. So position 1, 0, 1 is already a 1. Position 0, 1, 2, 3, this position 3 is also a 1. And so when you ask, is D a member of the set? The filter says yes, but this is actually a false positive. Yes, these are both flipped to 1s, but that's because of A and C, and D just happened to get unlucky. So this is how the Bloom filter works, and this explains why they're false positives and no false negatives. One of the other things, by the way, that I did in this talk, because on Zoom talks, it's really hard to see people's faces, because either you see my face or you see the screen, but you don't see very much. So I decided that I was going to make my talk absolutely chock full of faces. So these are just 2 faces per page, and hopefully that makes it more exciting to look at. Okay, so that's the Bloom filter. I should also point out that Bloom filters don't support deletes. And this is because on a delete, how do you know whether you can, which ones get decremented? How do you know whether you can decrement a 1? So if we decide to delete C, well, C points to 1, C points to this position here, position 3, and this position here, position 5. Can we turn these back to 0s or no? Well, remember when we first inserted C, there was a collision somewhere. And so one of these has to stay a 1, but we've forgotten why, because we no longer have the elements. We just have this bit array. So the Bloom filter does not support deletes, and that's often a problem. Okay, so this is the Bloom filter. Let's talk about how much space is used. So if you have a false positive rate epsilon, then the number of bits per element is a little bit more than 1, 1.44 times log base 2 of 1 over the false positive rate bits per element. And, so use this example, if you plug in, a 2% false positive rate, then it's about 8 bits per element. And this is about the common rule of thumb that you kind of want to allocate about 1 byte per element, for a filter. And this is a face for no reason. Okay, so that's the space usage of the Bloom filter. And Bloom filters are just absolutely all over the place. Computational biology, databases, networking, storage systems, streaming, they're used all over the place. And this is a picture of a system builder. And this is supposed to be a picture of the system builder's toolbox. And there aren't many data structures that are in a system builder's toolbox. Yeah, you need hash tables and balanced trees and B trees, but the other one is filters. And filters are used everywhere. And it's just an important tool that you need to know if you're going to build a system. And, it's cited all over the place. Okay, so Bloom filters are ubiquitous. And now let's see what we've talked about so far. I've described what a filter is. I've described what the Bloom filter is in particular, but this is from a while ago and stuff has progressed since then. Now we'll talk about how filters are used. And I guess this is a picture of how filters are used. Coffee just runs right through me. I'm not sure that's totally appropriate for a talk, but I really enjoy it. So I like that picture. Okay, so this is the talk so far. And what we're going to do next is talk about how filters are actually used. Are there any questions that people have so far? I don't know whether, can people even unmute or just panelists? Or, yeah.
I think there's some comments in the chat, which I don't know if you can see or not.
I think I'd rather have you or somebody else interrupt to ask whatever questions you think are most appropriate.
There's a comment that counting filters can handle delete. And I think there were questions from a little bit ago about what about false negatives, but I think you addressed that back some odd slides ago.
So that's a great question. Yeah, so that's a great comment about counting filters, that they do handle deletes, but they pay a big price. We'll talk about this later, but there is something called a counting filter, where what you have in the counting filter is instead of just having a bit array here, you actually have a small counter. You don't have to count that high, but it's still a small counter. And the result is that it does allow you to handle deletes, but it also takes more space. Like you're nowhere close to this bound anymore. But yes, it does handle deletes. But it'll be nice to be able to handle deletes without having to waste space. Okay, so let's talk about some places where filters are actually used. And often they're used to filter out queries to some large remote dictionary. And again, Seth, if you don't mind looking at the comments, and as you see fit, just say the questions out loud so I don't have to pay attention to that. So the filters out queries to some large remote dictionary. So here's a picture of a filter, which is like, say, a local data structure, say in RAM. And the large remote dictionary maybe is a database or key value store that's stored on disk, stored remotely. And so querying this dictionary is very expensive. But if you look here, say we're querying for A. Well, the filter says A is not in the dictionary, so the query gets filtered out. It becomes cheap because it's a local answer. Is B in the dictionary? Nope, it's not. Is C in the dictionary? Yes, it is. Well, now you need to go to the dictionary to look up whatever information you want. Is D in the dictionary? Filtered out. Is D in the dictionary? Okay, well, here we have a false positive. So we actually do need to go to the dictionary, and the dictionary says, no, it's not there. Is F in the dictionary? It says no. So this filter is actually filtered out most of these queries. We don't need to ask remotely anymore. The only one that got through that shouldn't have is when we were querying for this element E. And everything else, the filter answered correctly. And so it saved all of these expensive remote queries to the dictionary. So that's a filter use. And so the speed up is impressive because say you've got a workload that has P positive queries and N negative queries, and we want to look at how many remote accesses we've had to this dictionary here. Well, without filters, you need to do a remote access for a query, all the positive ones, all the negative ones. If you do have a filter, then you need to access all the positive queries, but only an epsilon fraction of all the negative queries. And that is a big improvement. Okay, so, and actually I'll do another example of just to illustrate how big this improvement actually is. So one common place where filters are used is in a data structure called a log structured merge tree. And a log structured merge tree, it supports really fast insertions. And the way it does it is by partitioning a big dictionary into a bunch of independent dictionaries. So I'm not going to explain in this talk why it supports fast insertions, but it's important. But the result is that instead of querying in a single dictionary, suppose you're querying like is B, we're querying like is B in the dictionary. So you need to query in all of these different dictionaries, the biggest one, the next biggest, the next biggest. You need to query in all of them. Is B in the dictionary? Well, without a filter, we have to do 1, 2, 3, 4, 5 queries. But with the filters, you know, this query is filtered out, this one's filtered out, this one actually gets through, these others are filtered out. And if you change the false positive rate appropriately, if B is not in the dictionary, you almost never need to do these remote queries. So the filter actually, because of data structures like log structured merge trees, the filter actually has a disproportionately sort of great improvement in the performance of the data structure. So this is showing how filters help queries in log structured merge trees.
So there's a comment in the chat from John saying, very related to group testing, is the main difference that there's a much higher emphasis on storage. And I guess we have more flexibility here. We're not stuck with an OR operation like the Bloom filter uses. Or I guess the point is he's asking for a comparison of group testing algorithms to what you can do with Bloom filters.
So that's a great question. It may be that all I can do is say that it is a great question. I haven't really thought about what the connections are, but it's interesting. That wasn't, I'm still trying to think if I can answer something better, but probably not. All right, talk so far. I talked about filters. I said what the Bloom filter was. I gave an example showing how they're used and sort of went several levels deep into how they're used. So I said the talk title was Time to Change Your Filter. And now I'll explain this. And this is, I love this cartoon. You know, Darth preparing for the big date, and there Darth Vader is changing his filter. Okay. All right. The problem is that the traditional filter is the Bloom filter. And the Bloom filter does have a bunch of well-known limitations to its capabilities. So one of them is no deletes. And one workaround is just, well, if you need to delete stuff, just rebuild in bulk. Another limitation is that you don't get to resize. You sort of have to guess n. That determines the size of your bit array, and then you rebuild if you happen to be wrong. And I even saw an application where because they had no idea what N was, they built the Bloom filter knowing that the N that they were guessing was far too big. Then they had an array that was almost all zeros, and then they compressed the bit array. And that just feels like the wrong way to do it. You'd really like to be able to resize so there's so that even when the number of elements changes, you're still efficient. Okay, so no filter merging or enumeration of elements. I don't really know what the workaround is for Bloom filters, and I'll explain more about what I even mean by this later in the talk, especially if people ask questions. And the other thing is that there are no values associated with keys in the Bloom filter. Now, often when you have a dictionary, what you're storing is key value pairs. And so if you're storing key value pairs, then you might want to have values associated with the keys. And Bloom filters can't do this. And sometimes you really want it. So the Bloom filter limitations increase system complexity, they waste space and slow down application performance. Just to be clear, this is not a unique observation of me. Like lots of people have made this observation, and the result is that there's lots of work trying to overcome these limitations. I guess I can also talk about some limitations in terms of suboptimal guarantees. So the Bloom filter is a constant factor off of optimal ends of space usage. There's this 1.44 versus just a 1 in terms of space. The CPU cost is suboptimal. Like it depends on log of 1 over the error rate, and it can just be constant. And also the Bloom filter has poor data locality, and you can get optimal data locality. So the Bloom filter limitations increase the system complexity, waste space, and they slow down application performance. Okay, so, well, the Bloom filter is a fantastic data structure, but there's other things to use instead, and we'll talk about that. So I also hinted at this earlier, there's tons of research on extending or improving or replacing Bloom filters. Like either if you want to have deletes or counting or have keys or filters on SSDs or asymptotics or engineering or adaptivity. And there, this isn't a very good chunk of related work because there's lots of other topics that people talk about for improving upon Bloom filters that I haven't even added. It's a very big area. But the point is when too much stuff is growing on your filter, yeah, it's time to change your filter. Okay, so talk so far. Well, I'm going to explain how to change your filter. So, and here is this picture. Somehow there seems to be a coffee theme to this talk, which maybe is appropriate if you're in Singapore and it's early in the morning. I see you change your filter about as often as you change your mind. Okay. So I couldn't find the right talk title. This talk, or parts of this talk are about a year old. And so when I was first making this talk, I couldn't find the right talk title. And I was thinking what it should be. And then I received this email. And the email said, "It's time to change your filters. Michael, welcome to our convenient filter reminder program. It's time to replace your filters, et cetera, et cetera, et cetera." And I snapped into action and ignored that email. But it turned out that wasn't the only email that I had received, which was basically telling me my talk title. Have you forgotten to change your filter? Have you forgotten to change your filter? It's time to, et cetera, et cetera. And so I finally said, hey, that sounds like a great talk title. And that's actually where the talk title came from. And I guess Home Filter Club, because we're all giving this talk and listening, from home. Okay, so so that's the title of the talk. It's time to change your filter. And a lot of the talk, I really just wanted to be a tutorial-like introduction to filter, and then I'll describe results afterwards. And I wanted to give a general technique for solving filter problems, and how to make like a whole constellation of different kinds of filters using the same technique. These are the three heroes of the talk. One of them is fingerprinting, and one of them is quotienting, and one of them is collision resolution. And so this is supposed to be the icon of fingerprinting. You know, this is the, you know, a whirl, and this is nose. And does anybody recognize who this is?
Ilya says in the chat, Knuth.
Yeah, that's Knuth. And that's because this idea of quotienting, which is the second hero of the talk that I'll explain, actually came from Don Knuth. So it's a very old and very powerful technique. And if, you know, this is a face that's a couple years old in the news, and it's also in US news. So this is Robert Mueller, and when he was investigating, well, so this is for investigating collusion resolution. I don't know if anybody else enjoys that, but I enjoyed it. So that's put it in there. And if we've forgotten about it, or it's just politics within the United States, so much the better. But I decided this is actually a better icon for collision resolution. So we're going to see these are three heroes of the talk, and I'll explain all of them going forward. Okay, so the first hero is fingerprinting. And so this is an icon showing that I'm going to be explaining what I mean by fingerprinting. And this is used in lots and lots and lots of different techniques for building filters. And this is just a partial list. So suppose that we want to make a filter of some set S. So what we're going to do is, so here's our set S. It's a dictionary with these elements x1 through xn. And what we're going to do is have a hash function. H, you know, this is our hash function. And what the filter is going to do is store hashes of each of the elements in S. So if S stores x1 through xn, then we're going to store the hashes h of x1, h of x2, all the way up to h of xn. And I will explain in the next slide or slide or two that these, in fact, can be stored more compactly than you can store a Bloom filter. And I'll explain how to do it in a second. So the dictionary stores the elements. The filter is going to have a compact representation of hashes of the elements. Okay, so this is the first, I'm just beginning to explain what we mean by fingerprinting. And I guess the point about this slide is really just this last line, which is, I just want to mention that this filter is just a dictionary. Instead of storing a dictionary of elements, it's storing a dictionary of the hashes of elements. And so it's just a dictionary, but it's a more compact one. So that's why this is a tinier thing than that one there. Okay, so this is what we mean by fingerprinting, is storing a bunch of fingerprints, hashes. And so now when we want to query whether some element X is in our set S, well, we first check whether the hash of X is in the filter. And if the hash of X is in the filter, we say yes. If the hash of X is not in the filter, then we say no. So instead of checking for the element in the dictionary, we check for the hash of the element in the filter. And yeah, and this is just a repetition, this can be stored more compactly than a Bloom filter. So now let's talk about the false positive analysis of fingerprinting. So the only source of false positives is hash collisions. So suppose that, so what does it mean for Y, some query element Y, to be a false positive? Well, Y is a false positive if, when we query for Y, well, okay, so Y is a false positive if Y is not in the set, but there's some hash in the filter that equals the hash of Y. So then it's a false positive. And if so, that means like if Y is in the set, well, Y's fingerprint will be in the filter, so that's great. That's a true positive. But it's a false positive if Y is not in the set, but there's a hash collision, and so we say yes. Now, these fingerprint collisions, these hash collisions, are the only source of false positives. Everything else, no source of false positive, just fingerprint collisions. So let's analyze the what the probability of fingerprint collisions is. Okay, so in this picture, what I have drawn is, so this is the element X, and the element X takes log of the universe size bits to represent, but even this doesn't matter. So this is the element X. Now we hash to a fingerprint, and the fingerprint is going to have log of n, the number of elements in the set, divided by the false positive rate epsilon bits. And just to explain this, the probability that any two elements collide, well, two elements collide if they collide for every single fingerprint bit. So the probability that two elements collide is one half to the power the number of bits, log of n divided by epsilon, which is just epsilon over n. So this is just the probability of a single pairwise collision. But Y is a false positive if it collides with at least one of the n elements in the set. So the probability that some element which is not in the set is a false positive is the probability it collides with one of these n elements, and so it's less than n times epsilon over n, and so that's where the false positive rate comes from. So this explains why it's why a fingerprint needs log of n divided by epsilon bits to get a false positive rate of epsilon. But now what I want to explain is how to store these fingerprints compactly, right? So the fingerprints are log of n divided by epsilon bits per fingerprint, but we can store them so that the number of bits per element is just log of 1 divided by epsilon. So log of 1 divided by epsilon, not log of n divided by epsilon, plus some constant number of additional number of bits per element. So this is what I need to explain next. And so this is the next technique of quotienting. So we've talked about fingerprinting, now we'll talk about quotienting. Okay, by the way, are there any more questions that I should field?
Chat looks quiet for the moment, so.
All right. But yeah, if something pops up, I'd love to hear it. Okay. So space, I'm going to explain why the space is log 1 over epsilon, or I'm going to explain how to get log of 1 over epsilon bits per element. And the way we're going to do this, remember we started with the element, then we got a fingerprint. And now we're going to divide the fingerprint into two pieces. Remember we said the fingerprint was log of n divided by epsilon. So that means there's a log n bits plus an additional log 1 over epsilon bits. That's the whole length of the fingerprint. This part of the fingerprint, the first log n bits, we're actually going to store implicitly and we're only going to store these these green bits explicitly. So these first log n bits, that's called the quotient. This is called the remainder. And this quotient, Q of X, we're going to store it implicitly. Actually, maybe I should show you on this picture here. So in order to store one given hash table, Q of X is going to determine a location in the hash table. So we've got some hash table of length n. So it takes log n bits to determine a location in the hash table. And so once we have this location in the hash table, now we're storing these Q of X bits implicitly, and all we need to do is store the remainder. And so by storing these log 1 over epsilon bits in a location which is determined by these log n bits, we do this for all of the elements, and now on average it's just log of 1 over epsilon bits per element. And this is called quotienting, and Knuth wrote about it decades and decades ago. So I guess I hope if people want me to re-explain something, that's also something to put into the chat. I'm happy to do that.
So there are a couple of questions in the chat right now, though perhaps about what
Sure.
was from a few slides ago. But so the first question
That's
here
okay.
was by Roland, who was saying you need a random hash function which takes different numbers of bits. As in, I guess he's asking, it's not a fixed size. You need a not a fixed size hash function, one that takes different numbers of bits as input.
I think that's not that big a concern. I'm not sure you need that many different numbers of bits for the hash function. Because first of all, you can always just take more bits than you need. Hash to more bits than you need and just take the ones that you actually need. But I guess I'd have to know a little bit more about the context of the question.
Okay, and the next question is, let's see, so Niji, how does using a fingerprinting function H on the Bloom filter with hash functions F1 to Fk differ from using an ordinary Bloom filter with hash functions H F1, comma, ... HFK, H composed on the left? I'm trying to understand exactly what this means. A fingerprinting function H on the Bloom filter compared to an ordinary Bloom filter with composing the hash functions with the functions.
Right. So my guess, I hope I'm answering the right question, but what I think he's saying is that you could take a Bloom filter, but instead of just storing a bit array, with zeros and ones in every position, you could put a fingerprint there or something like that. But one of the things that you'll see is nice about this approach of explicitly storing a single fingerprint is it also means there's a nice place to put a key if you want a key. Like the element that every time you've added a single element, you're sort of just storing the fingerprint basically in one place in the data structure instead of smeared out around the data structure. And that also makes it nice for insertions and deletions and or enumerating all of the fingerprints that are in your data structure.
Okay.
But again, I still think it's a very good question, and there are reasons why one might want to do something like that. And there are lots of different applications of filters, and so it's an exciting space where there are lots of sort of different possible designs we can do. And so, like, my point in this talk was kind of to show some of the moving parts that there are, but it's only some of them. Yeah, go ahead.
Okay, next question here from John. Did the analyses on the previous slide with log n over epsilon assume fully independent hash functions?
So that is a great question. These are really good questions. So so I have basically been assuming fully independent hash functions. And part of the reason why is from a practical point of view, it doesn't matter. If you want to use a cryptographically secure hash function or anything, that's as good as we get. Now, I do think that there's a lot of interesting work that either to be done or done about showing how you can use other kinds of hash functions, either with limited independence or with tabulation hashing, in order to get these guarantees. Like my guess is that these guarantees would also apply with other sorts of hash functions like tabulation hashing. And it's just not something that I have focused on. But that's a great question.
There are a few more questions here. Should I keep going with questions while we're paused here? Do you want?
Sure.
Okay. So
sure.
the next question is it possible to get rid of the false negatives? And there was an earlier comment about by using another filter in conjunction or inverting things, different hash functions, and so on.
So, so there aren't there are false positives. There are no false negatives. I think what the question could be asking is, if you allow for false negatives, is there any way you might be able to do better? Or maybe the question could be saying, is there any way to make it so that we have false negatives but no false positives, or something like that?
Or perhaps asking no false positives or false negatives.
If you have no false positives or no false negatives, then you're actually just storing the data, the dictionary. Do I mean that? So I don't fully mean that, actually, because it also depends if you want to, there are ways that people somehow have a filter with false positives and then with negatives. So I'm not right. Part of it depends also if you're talking about a static data structure or a dynamic data structure. If you have a static data structure, you already know what the set is, and then you build the set, and then you have a filter, and then you sort of correct all the false positives, in order to, to avoid having any errors. And I think that there are ways of doing that. Most of what I'm talking about in this talk is actually going to allow for insertions and deletions, even though so far I haven't been talking very much about that. But ultimately, in most of the applications that I care about, I also want there to be insertions and deletions.
Okay. Let's see, one more question. Does quotienting support resizing the dictionary? Is Q of X the relative location of R of X in the fingerprint dictionary, or the absolute location?
So these are really good questions. I'm impressed. I wish I could actually sort of meet the people who are asking them. The answer is that, actually, how about I answer that in one slide or two? So Seth, please nag me if I don't answer that, because I think it'll make a little bit more sense, if I proceed.
Okay. The questions here continue. The coverage so far has focused more on the space usage of filters, more so than the exact false positive rates, accuracy of the filters. Is this because the space usage is more important for practical usage?
Both are important. In general, for practical usage, mostly what I've seen is you sort of want to have a false positive rate that's like 1% or on the order of 1% or 2%, something like that. The reason why I haven't focused much on the false positive rate is because it's kind of easy, in the sense that, well, if you want a false positive rate of epsilon, this is how many bits you need to store per element, log of 1 over epsilon, and you'll also see plus a constant additional, like plus 2 additional bits. And I'll explain that in a second.
Okay, that looks like it is it for questions right now. So,
Sounds great. All right, so let me just say where we are now. So we've got our fingerprint, which is log n plus log of 1 over epsilon bits. But these bits here that are in green, these log 1 over epsilon bits, are the only thing that we're storing explicitly. And these log n bits we're storing implicitly based on the location in the table where we're storing this remainder R of X. So this is how we, based on the location and the bits that are stored here, that's how we get this fingerprint. And we store a whole bunch of fingerprints in a hash table, and that's how we store everything. But the problem is, how do we deal with collisions in the hash table? So what if one fingerprint, we're storing, so what if, so there's some element X and Y where when we look at the fingerprint H of X and the fingerprint H of Y, they have the same quotient here. So they want to be stored in the same position in the hash table. So how do we deal with this? And well, it's very easy in general to deal with collisions in a hash table. Isn't this a solved problem? And the answer is, well, I mean, yeah, that's what linear probing does. Or, just plain out of the box linear probing. If the current location is filled, you go to the next position. So why not do that? And the problem is, well, is shown in the slide when we have hash collisions. So in this example, we've got a 6-bit hash, and the hash table has 8 positions. So that means we've got 3 bits for the address in the hash table and 3 bits for data. And so if we look at this first position here, this first position here is representing the fingerprint 000 001. And there's no ambiguity there. But now let's look at this, what's stored in the second position in the table, 011. So what does this 011 represent? Maybe it represents the hash 001 011. But on the other hand, maybe this 011 shouldn't actually be stored in the second position in the hash table, and really it wanted to be stored there, but then it got shifted to the right. So the point is, and same thing here with this element, maybe this element really wants to go in the previous position, or maybe it wanted to go here. And there's nothing in this hash table that's actually explaining. So the point is that because part of the hash is stored implicitly based on location, how do we change the location? And that's what I'll explain next. And this is with like this third hero, which is collision resolution. And there are lots of different ways of doing it, and I'll explain one of them. Okay, so just a reminder of the talk structure. I talked about filters, how they're used, limitations of Bloom filters. And I'm talking about these 3 heroes, fingerprinting and quotienting and collision resolution, which are used in lots and lots and lots of different kinds of filters. So there's variants of quotient filter variants and cuckoo filter variants, which is another kind of filter I'll talk about a little bit. And lots and lots of filters that use different approaches. This bottom column here is different approaches for collision resolution. Okay, so what I'm going to do now is talk about the particular form of collision resolution that was used in quotient filters, which is a particular kind of filter. And I'm going to show that if we use 2 metadata bits per slot, then we can actually recover the original location of every element. So this column is the first group of metadata bits, and this is the second group of metadata bits. So if there's a 1 in this first column, What that means is something is hashed here. And I'll explain what I mean more by that later. And if there's a 1 in the second column, it means I'm hashed to the same place as the element before me. So, and the way we have to decode this chunk of array elements is starting from the top. So we can't just go, we have to start from the top here, and then we're going to decode like sort of unzipping a zipper somehow. So let's look at this first array position. There's a 0 here, which means nothing is stored in this position. And so, there's no, we don't have to worry about what bits are here because they're garbage bits. This is an empty array position. We look at the second array position here, and there's a 1 that's hashed here. That means something is hashed here. So it's the first thing in the array. So we know that 0, 0, 1 is the remainder that is hashed here. And so we can decode. So 0, 0, 1, 0, 0, 1, that is one of the fingerprints in the hash table. So now let's look at this second position. There's 0, 1, 0 that is hashed here. We look at this bit, the second bit here, there's a 1 in this position here, which says I'm hashed to the same place as the element before me. So that means that this 0, 1, 0 remainder is hashed to the same place as the previous element, which means it's hashed here. So I guess I should have been saying this. So no element is stored before its target position. This is an empty slot. That's what I should have said. I said, this is saying the remainders in the second slot. And now this remainder is mapped to the same location as the previous remainder. So this is actually encoding 0, 0, 1, 0, 1, 0. And that 1 here is saying the remainder is mapped to the same position as the previous remainder. Same here, this 1, 1, 0, that 1 is saying that the remainder is mapped to the same location as the previous remainder. And so this is encoding 0, 0, 1, 1, 1, 1. So now that metadata bit is a 0, which means this remainder is mapped to the next array position. And the next array position is this 1 there. And so therefore we know that 0, 1, 0 is mapped to the next 1 in this metadata array, and so forth. The remainder would map to the next position, but there is none and it's empty. And the reason why there is none is because no element is stored before its target position. And so this remainder is in the correct slot, and so forth. Remainders mapped to the same location as the previous. So the details don't matter, except that it's cool actually to do the example and see this actually work out. And you see, you start from the array position, just decode the entire chunk from left to right. And so when you're actually implementing this, you implement the array in little chunks, and so you decode little chunks at a time, and then you have a whole new chunk, because you always, again, in order to decode this, you see you have to start from the top and zip all the way down to the bottom. Okay, so let's talk about the additional capabilities you have with this sort of decoding. Well, you can now count and implement deletes. Talk about, there are lots of different ways of doing counting. We could talk about that more at the end, but there are different ways of doing counting. One way of doing counting is just to encode in unary, where if the same element occurs 5 times, just insert that same fingerprint 5 times and the hash table could deal with it. But there are more sophisticated ways of doing that. You can also resize. And now I can answer the question that about what happens if you want to resize the table. Suppose what you want to do, suppose you've added more elements to your table. And so now you have enough elements that you want to double the size of your hash table. Well, if you double the size of your hash table, that means, so n has doubled, So that means log n has increased by 1. So that means when you double the size of your hash table, the quotient grows by 1 bit and this remainder shrinks by 1 bit. When you have the size of your hash table, because you have the number of elements, then you store one additional bit gets stored explicitly in the remainder because the hash table is half the size. And so instead of being log n, it's log n minus 1. And so basically resizing just means changing the size of this hash table where you store the fingerprints, and then the remainder, which is the part of the fingerprint that you store explicitly, increases by 1 or decreases by 1. And you can also do element enumeration and filter merging. And this has turned out to be much more important than I would have expected. Just the ability to take all the fingerprints in your filter and say, merge them with the fingerprints in a different filter. And that turns out to be a very, very important thing. This is actually much, much more important, for example, than supporting deletions. Like deletions, I haven't seen that many uses of, but this I've seen a lot. And then keys can also have values because since you're just storing the element in one place in the array, you can actually, store a value with the array. And I think I drew a picture like this, right? Along with your element, you can have a value and you just store that in the array as well. Okay, so this is talking about quotient filters, and there's some theoretical advantages where if you implement it correctly, you can make so that the CPU cost is constant instead of something that depends on the false positive rate. The data locality is much better because when you have a Bloom filter, for example, you're probing all over the filter. Whereas in this particular data structure, you do a hash for the right position in the hash table, and you just have to scan the same way you would with linear probing. So the data locality is really good because it's just one probe and then a small scan, possibly. And the space also turns out to be asymptotically better. Or not the 1.44 turns into a 1. Okay. So I think what I'd like to do, are there more questions that have come up that I should field? Because that would be a great time.
So there was a question from a little while back on, I'm not sure what it's referring is there what happens if something is inserted at 100? I think asking like what happens if something is inserted a lot later in the table in the quotient filter. Maybe this was in reference to, do you have to search the whole, scan through the whole filter to read it, or 100, sorry, maybe not 100 but 100. Excellent. That's in the binary location.
Let's see.
In the example, what happens there you go. Mm-hmm.
Oh, if something is inserted here
At 100.
Right. So good. That's a good question. So we're actually storing all of these elements in sorted order using some, basically using Robinhood hashing. And so if we would store something in 100, if it's going to go in this position, then, well, this remainder is already useful. Actually, let this go through. So if we're inserting something here, this position is already used. This position is already used. And so we would actually use this position where the mouse is going back and forth. The other question that somebody could ask is, what happens if you decide to insert something else here, like in position 0, 0, 0, 1? And if you insert something else here, then you'd have to push a bunch of these remainders to the right to open up a hole to make space for it. Because for this encoding to work, everything has to be inserted in sorted order. And it also means that if we delete something, we need to compactify.
Okay.
So that's a great question.
Another comment about I understand the theoretical advantages, but what are the practical trade-off versus Bloom implementation? Say it's just a classic Bloom application.
So, so I guess that's a great question. Again, I know I'm being repetitive, but I really think these are fantastic questions, and I'm very impressed. I'm also curious to know whether people would be asking these questions if they had to show their faces, or if the anonymity makes it easier.
At least some of these people I know, and they tend to be active in in-person seminars as well. So I can vouch for them.
All right, I'd love to meet them. So the answer is, so the quotient filter turns out to be hard to program. I've programmed this in a high-level language, which is called Graduate Student. Prashant Pandey right here did most of the heavy-duty programming, and also Rob Johnson, who is a senior person who, and so this is not easy to program. Whereas the Bloom filter is really pretty easy to program, relatively speaking. And so programming this is much harder, but it runs much faster because the data locality is so good. And then there are all of these other advantages where, as I said, often with applications, there are things that you need, like you don't know exactly how many elements you have. And so you really do need to resize based on how many elements you have. And Bloom filters don't allow that. And that's really, and so many actual applications that use Bloom filters have to turn themselves into pretzels because they don't have resizing. And I gave the example earlier in this talk about an application that used a Bloom filter and then compressed the Bloom filter because it was mostly zeros. And we just shouldn't be doing that. You should just be resizing. And then element enumeration is because often, like maybe you're collecting a bunch of different elements in different parts of your system or your data structure. So you've got the elements stored in two different places. And so you've got two different filters, but then you want to merge these two elements, these two groups of elements together. So you want to merge the filter. And this is very common. So so basically the quotient filter is something that generally works very well in applications that use Bloom filters, and sometimes it simplifies the application so they don't have to tie themselves into knots because of the limitations. So let me just describe what I've done so far, and then I'm just going to go a little bit farther in the talk, and then I'll end. So we talked about fingerprinting. I said that the false positives only come from fingerprint collisions. We talk about quotienting, where we store these fingerprints in the hash table implicitly. And so the login bits of the fingerprint just depend on the hash location. And then we talked about collision resolution, which is, since you're storing these fingerprints in a hash table implicitly, you have to deal with collisions in the hash table. And the same way that there are different hash tables that solve collisions in different ways, there are different filters that solve collisions in different ways. And I like this quotient filter approach, but I also like some other approaches. So an alternative is something called the Cuckoo filter, which is based on a Cuckoo hash table instead of based on linear probing. I'm trying to decide, let's see, do people want me? I can go into this pretty quickly and I can skip it. Is there any way to get the temperature of the room? Because I'm already running over. I won't run very far over, but do people want me to present this, or do people want me to Zoom? I know that's an embarrassing question to ask. Seth, do you have any advice for me?
I don't know how we can get feedback from anyone. If there's a thumbs up or thumbs down, they can click on or something. But I don't know. But you have a few more minutes, so.
All right. I guess I'll go and sort of zoom slightly through this, but not too much. So I'll talk about how you can go from cuckoo hashing to cuckoo filters. And so it's the same idea of using quotienting, and it's just we're going to solve the collision problem in a different way. So cuckoo hash tables are a beautiful hash table where you have two hash functions, and each hash bucket has some number of slots. So these here, I've drawn 4 slots. So 1, 2, 3, 4, that's the first hash bucket. That's the next hash bucket. That's the next one. And so each element has got 2 different hash positions where it can go. And this is supposed to be a picture of a cuckoo bird. And if there is space to put the element in one of these buckets, you just put it there and you're done. But if there's no space in any of these 8 slots, then you kick out an element and move it to the alternative location. So, and this is what I've shown here. There was no space in any of those buckets. So this particular element here got kicked out. Now there's a new location where we can put this element X. But now that we've kicked this element out and moved it to our other location, it could be that that also kicks out another element from this bucket, which goes someplace else. And it's named Cuckoo filter, which is just a wonderful name because it's reminiscent of cuckoo birds who lay their eggs in another bird's nest. And then when the cuckoo birds hatch, they hatch first and they're stronger and they push the eggs and the other hatchlings out of the nest, which is kind of cool that it evolved. Okay, so this is a cuckoo filter, a cuckoo hashing. But now let's talk about the obstacles for a cuckoo filter. So suppose instead of storing the element X, we want to have 2 different hash functions. So X, so there's a hash function H of X and a hash function, sorry, H1 of X and H2 of X, and X could go in either of these 2 positions. But suppose that we choose one position and then we need to get kicked out. How do we find the alternative location when we're not actually storing X? Like if we were storing X, then we could try both of these 2 hash functions. But if instead we're just storing a hash of X, how do we find the other hash of X? And the answer is, well, we actually give up on storing 2 independent hash functions. And so the alternative location is just going to depend on this first hash function. And what's interesting is we're also going, on one hand, we're actually going to give up on asymptotic correctness. And so if when you have a cuckoo filter, as n gets very, 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 very large, impractically large, the cuckoo filter will stop actually working. But for all practical values of n, as well as values of n that are even larger than practical, it still works. And so it's sort of amazing that you've got this data structure that in general sort of doesn't work, but for anything that we would actually care about, it does. And that's a cuckoo filter. Now, what's interesting about the cuckoo filter is it seemingly doesn't have any metadata bits, but actually they're sort of there because since there are these 4 slots per cell, then 2 more fingerprint bits are stored explicitly because I'm not sure whether I'll go into the details, but basically because the quotienting isn't as efficient. And so it's basically the same size as what I described before. So if we can compare these 2, in both cases, the space is great. The quotient filter is slightly better data locality, maybe, but they're both good. Quotient filter has some degradation at high load factors. Cuckoo filter degrades a little bit more at high load factors. Cuckoo filter is really good at searching, so some better in practically speaking than the quotient filter. They're both fast at inserts. Quotient filter, maybe supports more values and multi-sets and values and deletes. Probably that can be added to the Cuckoo filter as well. The Cuckoo filter code is easier. The quotient filter, I said, is complicated, and so on. So they're both sort of using at a high level very similar techniques and just a different way of hashing the fingerprints. Okay, so I'm sort of nearing the end. Basically, there is like an optimal filter whose space is sort of 1 plus little o of 1 times n log 1 over epsilon plus like these are the metadata bits, and basically you can get the space really, really, really close to the theoretical optimal value. And you can support inserts and deletes all in constant time with a great error rate and have great locality reference and so forth. I think I wanted to end with one empirical slide and then a conclusion slide, which is basically describing how different data structures perform as the load factor gets higher and higher. The load factor is how full the data structure is. And sort of as the data structure gets fuller and fuller and fuller, what happens to the performance? And so this is measuring throughput. And this is for insertions. And we want good throughput, so higher is better. And you can see that when the data structure is mostly empty or not too full, the Cuckoo filter is really, really good. And then what you see is as the data structure gets fuller and fuller and fuller, which means more and more space efficient, the Cuckoo filter starts to perform worse and worse because all of these kickouts, like basically the kickout chains get longer and longer and longer. And so the Cuckoo filter starts to perform more poorly. And so different data structures perform differently as you fill them up. So this was the performance of a particular quotient filter, and you see it also degraded. And this is sort of an alternative quotient filter where you also do a kind of minimum of 2 choice technique. And you see that there are things that you can do that mean that the data structure really performs well, even when it is very full. All right, so that's the empirical.
There's a question here about what a Bloom filter would look like on this graph.
So Bloom filter would be much worse. So I think all of these are different data structures that are really good ones that are all sort of top of the line sorts of things that are all kind of kicking the Bloom filter. And so that's why it's not even mentioned here, because it's much worse than the others. But that's a great question. This is showing the performance on queries. And you can see that for queries, like the Cuckoo filter suffered a lot in its insert performance as it was very full. You see, on the other hand, that for queries, it really kicks butt. And the vector quotient filter, which was like the best in the other slide, is also pretty darn good. Not quite as good as the Cuckoo filter, but pretty darn good. Okay, I think I want to end. Oh yes. So does anybody know what this slide is? Seth, you've probably seen me give this slide before. Can anybody guess what this is?
Sakshi says, Dr. Seuss.
It is indeed Dr. Seuss. And the question is, why is it here besides the fact that I like Dr. Seuss? I think I'll just explain. This is my summary slide. And so this is the summary. First of all, the title was "It's Time to Change Your Filter." And I talked about fingerprinting and quotienting and collision resolution. It's sort of the unifying theme, both in theory and practice. And then I guess the final comment here is that applications should demand a richer set of operations from their filter. And that's what we also talked about. I don't think I have anything else I want to say here. Oh, yes. Nope, I think we'll stop there. All right, any questions?
Okay, thank you, Michael. So yeah, any questions anyone has? If you want to raise your hand and talk in person, I can enable that. So anyone has any questions they want to ask, or just say hi to Michael until he hears some voices. Okay, Roland.
Hi, Michael. Nice talk. We have sort of worked on a kind of application of Bloom filter where speed is very critical. So we are roughly maybe, I haven't measured exactly, but maybe 10 to 20 cycles per hash function. And maybe we use only one hash function or two at most. So let's say, 40 cycles. And no, we only need query and delete. It's useful to have, but rare. Right. So would any of these newer variants?
So I guess So
remember that it has to be really fast in terms of cycles.
So what is the application? Is it a networking application or a what?
It's a let me say it's kind of a secret application where you instrument the code, and the Bloom filter is used to check something. So it's like every function call you might need to check something.
I see. So my guess is
you have to be pretty fast, right?
Yeah. So if you were using a Bloom filter, it's likely that one of these data structures would speed you up substantially. But I'd be very happy to talk to you afterwards, and also put you and also introduce you to Prashant and also Rob Johnson, who were the real amazing coders on this project.
Right. So the point is that the O1. So I understand the theoretical guarantees but the O1 constants are probably sometimes dominant.
Yeah, in this case, it's not just a theoretical guarantee. And most of what I described most of the talk I gave is not about theory. It's sort of showing how you use theory and actually implement it. So the problem that Bloom filters have is...
Oh, by the way, we use counting. We are using counting Bloom filters.
It was you who made the comment earlier. Isaac, because you do delete.
But rare, very rare.
Concern? How much is space? Oh, I'd love to hear about this, because I'd definitely like to talk to you afterwards, because there's surprisingly few applications where people actually care about deletes that I've known about. And so hearing even one of them, is great.
That's why I say it's so rare. Yeah, you probably don't need it, but you keep it in the back pocket. Yeah, in the rare case that you do. So it's possible to have delete, but improbable.
Right. So I would be delighted to talk to you, and meet like on a different day. The problem that Bloom filters have, especially with just the naive implementation of a Bloom filter, is you've got a whole bunch of different hash functions, and you don't have good data locality. And
sure.
So,
and if you only use one hash function, then you don't have that problem.
So do you do something where you have, if you only do one hash function, but then you also don't have, then you have a high error probability?
You have a high error.
Or were you?
So there's a trade-off between that,
Right. And so the point is that you don't
accuracy
actually
versus
need,
time.
right, but you don't actually need that trade-off. Like you can get,
Right. So
So most
maybe we
of
could
the-
do a quotient thing, but the code seems complicated.
the code is complicated, but it's also already there. And so, and there's also code for like a lot of these filters. As I said, I would put you in touch with people who are experts on the quotient filter code, but there are also other people who have expert in all of these different codes. There's really great code out there.
I mean, maybe we should talk offline, because otherwise we are holding off things.
Yep.
My point is that when you have sort of very high performance requirements, then things may become more tricky.
Right. Well, these things, what I've described are what you do when you have high performance requirements. Like when you like, it's very hard for me to know what would be a case where the Bloom filter really is the best.
Right. But note here that I'm not talking about how many queries per second. I'm talking about like 20 machine cycles.
Yep.
That kind of performance, right?
Mm-hmm.
The query per second doesn't actually matter because the queries are more distributed throughout the program.
Yeah, I'd be very interested in learning about this.
Oh, we can talk offline.
Sounds great.
Yeah, it's a bit unfortunate we're doing all this remote thing.
Yeah. Well, one day I will make it to Singapore. I've wanted to do this for a long time.
Thanks.
Please, Michael. And next time you are here, Roland will guide you to a lot of local, very good food.
Yeah, I know. I mean, Singapore is one of the food meccas of the world. So I can't wait.
Yeah, Roland is a really expert.
Yeah, I know lots of people at Stony Brook, but I never actually got to Stony Brook.
Okay, other questions? Anyone have anything else? So I know David has a slightly longer question to ask, and I've set him up on talking permitted, but I guess you see if anyone have any quick questions or shorter comments. Okay, then maybe we will sort of call the seminar closed, and then let David ask his question. We'll treat this as offline or afterward the talk or whatever, so that we don't have to keep everyone here if they don't want to listen. So I'll thank Michael for his talk again. So thank you for coming, and again, you stick around for a second, answer David's question afterwards. That'd be great. And
absolutely.
Thanks. Oh wait, is there a last question in the chat here? So from the chat, we have a work in which we formally verify the exact false positive rate of a variety of filter structures, Bloom filters, quotient filters, etc., assuming independently random hash functions, and found that the false positive rates could be composed modularly. Do you think this kind of compositionality can be found in the asymptotics? This is from Kiran. So while you're thinking, I say so. So Ilya and Kiran here have been working on formal verification of Bloom filters and things like this, and have done some really nice work on the formal verification side. How do you actually make sure you show these filters are doing the right thing, and in terms of providing the probabilistic guarantees that we claim they are, and so on. Anyways, if you were here, I would love to introduce you to them, but if you haven't met them already.
Yeah. So I mean, I don't think I can give a good answer. I can only say formal verification is one of these areas that I wish I knew more about. And if I were a more virtuous person, or if I slept half the number of hours that I need, then I would learn about it. So I don't think I can say anything wise, except that, it's something that I wish I knew about. And I think it's an exciting area, and it feels like an exciting application.
Yeah. I think he was asking about strictly this issue of composition is what happens when theoretically what happens if you compose these things, if you compose multiple things together, and just do all the guarantees sort of fit together compositionally or something like that. Anyways, which seems interesting. Yeah.
I am not, there shouldn't be any huge gotchas with composing things, basically because the source of the false positives in the kinds of filters that I described is a very simple source, which is we're separating the source of false positives from everything else. And the source of false positives is simply you're storing a bunch of fingerprints, and there's a false positive when there's a fingerprint collision. And how we're storing the fingerprints is, complicated in terms of programming or even in terms of algorithmics, but is disjoint from where the false positive rate comes from. So I don't think that there's much in the way of a surprise about where the false positive rate would come from. It's just, storing a set of fingerprints.
Okay. Kieran says, I see, thanks. Okay, good. So as I said, let's go back to where we were before. Thank you again. Let's call the seminar closed. And David, you can ask your question.
Oh, hello. Hi. Hi, Michael.
Hi.
I actually attended your fast code talk in November 2020 on the same topic.
Oh,
yeah. So
yes, it looks familiar to you then.
yes. So I actually asked you a question during that talk, and I think I didn't explain myself very clearly during that talk last year. And I sent you an email after that with a scribble about so if you go back to your quotienting slide, you had this you needed 2 bits in order to chain up things, right? 2 extra bits.
Let's see. What slide?
Yeah, this slide. So you use 2 bits to do the collision resolution. So my question that time was, what if you just treat the quotienting, the remainder part as something like a bloom? You just take the OR of everything that appears there, and then you just do the analysis of the errors in that setting. Like you will lose the ability to I think you'll lose one ability, which is to resize, but then everything else will be very simple, right?
So let me, I'm almost under, so can you say this one more time?
So for example, in your, okay, let's just say this example. You have 0, 0, 1, 0, 1, 0, right? And you push that to the next row. But instead of doing this, if I just take the OR between 0, 0, 1 and 0, 1, 0, and I store it there. So I store 0, 1, 1 in the second row.
Oh, I see.
Yeah.
So with this one, you take the OR of, let's see, 0, 1, 0 and 0, 0, 1.
Yes.
And so you get 0, 1, 1.
Yes, and I don't have your 2 columns, the 2 additional 1 bit columns. So essentially the remainder part becomes something like the standard typical fingerprint bloom filter kind of analysis, right?
Right, it's looking more bloom filtery, but I'm concerned that you lose a lot of the guarantee because right now it seems like it's going to be much more likely to get a false positives, because right now the only way you would get a false, like a collision, is if you have sort of 0, 0, 1, 0, 0, 1, or 0, 0, 1. Here, let me just go like this. sort of 001, 001, or 001, 010, or 001, 111. Those are the only ways that you can get a collision. But you see here that there are, but on the other hand, suppose we took the OR of all of these three these numbers and stored it in one place, then we would have just 111. And now the probability of a collision, instead of being 1/64th, becomes sort of just 1/8, because these will all be ones. So I can imagine.
I mean,
I'm not
in this
saying,
example, it's not a really good example because you have 111 over there, so you will always collide, right? In this particular example.
yeah. So I think that it might have been, there was a question that Seth read out loud earlier that was like effectively somehow, is there any way of combining some of the sort of quotienting ideas with Bloom filtery ideas? And I do think that the answer to that is yes, and that it is possible to do that. But the exact thing that you said, I'm skeptical that it would work, but I suspect that there are other variations that might work. Also,
So,
what is the picture in your background? I have to.
the picture.
Where the mount.
What? Oh, I can't see my own
no.
picture.
I assume that's from Switzerland.
Oh, is it the non-camera version of the?
The picture of you in the snow.
Yeah, that's a picture in Switzerland. Yeah.
He spent a year or two and a couple of years in Switzerland.
Yeah, I was at ETH. Yes.
Got it.
Yeah. So actually, if we know the rough numbers of things to hash, which is n, then the first part of the quotient will make sure that we get a constant number of things in each row, right?
Yes.
And if we have a constant number of things in each row and the remainder part is log 1 over epsilon, if we and we assume that each thing is each bit is flipped independent of each other, then the probability of something getting false positive is kind of roughly epsilon, right? Is it not?
Yeah, let me think about that. It's an interesting idea.
Because the probability of false collision is 1 minus half to the power of things in that row, the whole thing to the power of the number of bits used for the remainder.
So I'm still concerned that this, as my understanding of your idea, it seems hard to make work.
Okay.
But the reason why is, again, this remainder here, like each of these is a 0 or 1 with 50% probability. So they're just random zeros or ones. So if we take the bitwise OR of 2 of these fingerprints and we combine them together, then now 3/4 of them are going to be ones. And so it feels as though I guess I can't tell. I'm going to have to I'll do some figuring, tomorrow, and because it would be interesting if it does work, and I can't tell.
I think he's thinking of the number of bits flipped as a constant, whereas the number of bits total is like log 1 over epsilon. And so if the bits flip, if the number of things that are flipping bits is if sort of a constant number of bits out of log 1 over epsilon are flipped, then maybe there's enough room. I think that's his intuition here.
So my intuition is roughly a constant number of things will be hashed into each row. So we just need to fight with a constant number of things flipping bits, and we have log 1 over epsilon bits to play with, right?
The concern that I have is that, I might not be understanding correctly. But the concern that I have is that when I have, like right now with this particular scheme, when I answer a query, it needs to be an exact match. But if somehow you're taking the bitwise OR of even 2 fingerprints, then it's no longer an exact match on a query. And so my concern is by not being an exact match, you're increasing the false positive rate a lot. Because, like, for example, like suppose that the fingerprint is 111 here. Then if the fingerprint is 111 with a bitwise OR scheme, if I'm understanding it correctly, then now basically this is a map that says, oh, like I'm going to accept anything that
touches this row. Yes.
Yeah. And so so my concern is that you're giving up.
But the probability, there should only be roughly a constant of things touching that row, and the probability of you getting 111 is 2 to the power of log 1 over epsilon, right? You need all the bits to be flipped to 1 for the example where you have one thing causing everything to be 111.
I will have to do the we'll have to do the math, but even so, it feels like you're wasting a constant, like you're wasting your space usage, like you're doubling the amount of space. Like to me, it feels like for some value of 2, you're using twice as much space as optimal.
I see.
So that's my concern.
Yeah. By the way, Davin's I think I may have mentioned that this last summer he spent some time looking at the constants on backoff protocols, trying to see what exists in literature and what can we do in terms of getting that constant down from 2 to 1.45 to 1.42 to whatever. Anyways.
Oh, very nice. Yes. Yes, I've definitely heard about you. So that's fantastic.
Okay.
Anyways.
Yeah. I can maybe forward you the scribbles again, and maybe this time it will appear in your inbox properly.
Sure. And I will also try to think about it myself. Because it's regardless of whether it works, it's an interesting idea.
Okay.
And I think it's a very interesting idea.
Yeah. Thanks for the talk and your time to answer the questions.
Cool. Okay. Well, thank you.